Boiler efficiency. So boiler will have normally two types of efficiency. One will be direct efficiency, another will be indirect efficiency. Direct efficiency calculation is like this: energy output divided by energy input. Okay, not here. Energy input. So in formula, if I write Q equals H, capital H minus small h divided by Q into GCV into 100. So Q quantity of steam generated kg per hour or kg per second, whatever you like, you can put. H is enthalpy of the steam, kilocalorie they have given, you can change unit also. H enthalpy of water. So here all calorie given, so they are using calorie, but if you can use, if you want to use joule, so that also you can use. Joule also energy unit, calorie also energy unit, heat is energy. GCV gross calorific value of the fuel. Okay. Now boiler indirect efficiency formula is this: 100 minus 1, 2, 3, 4. So one is dry gas, flue gas losses. This is losses actually. Initially you are assuming 100% energy is going. Now how much losses are there? So indirectly you are trying to calculate how much energy actually you are giving to your fuel, steam. Evaporation loss, evaporation of water formed due to hydrogen in fuel, evaporation due to moisture, moisture present in combustion. So all these parameters if you know, then you can add and minus 100 minus of all these losses. So in that way indirectly you can calculate boiler performance. So boiler efficiency, another formula we can write, eta equals heat output by heat input, heat output by heat input. Okay, IP I am writing, IP means input, O slash P means output. Input will be more and output will be less. So heat input minus heat loss divided by heat input. I can write H input Okay. So heat loss, H loss equals Hg plus Hu. So Hg stack loss. Stack loss means after burning flue gas going out to the atmosphere, so that loss, some energy it will take, so that loss is called stack loss. And Hu is radiation loss, because it is metallic system, so some radiation will be happening. Okay, radiation losses uncounted for and manufacturer margin. So manufacturer will also have some margin, so that much of loss you are adding here. So input and the efficiency becomes, so eta becomes Hi input plus Ha minus H loss divided by H put plus Ha. So Ha is added heat above 100 degree centigrade, added heat above 100 degree Fahrenheit to the combustion chamber. So because of that certain losses will be there. Combustion chamber. Added heat to the combustion by the steam, not combustion chamber, combustion air by the steam air heater. Okay, so sometimes steam will be heating inlet air, so that much of losses will be there. Okay, so that is added as a HA. So this formula also can be used if the data is given. For example, if input data, HA data, H loss data is given, then boiler efficiency you can calculate. Now we'll try to solve some problem. First problem is on economizer. An economizer has a feed water inlet temperature 160 degree, exit temperature 240 degree, flue gas inlet temperature 390 degree, exit temperature 220 degree. Efficiency of the economizer I have to calculate. So, T I can write here TWI, economizer has feed water, TWO exit, flue gas TFI, TFO, and then you have to calculate eta economizer. Okay, so TWI, how much energy it is taking. Okay, so TWI minus TWO minus TWI, MC, I can write like heat, some to increase heat. So heat equals MC delta T, mass specific heat into delta T means temperature difference, temperature rise. Okay, now here is another problem. An economizer has the following data: inlet gas temperature 255 degrees centigrade. So TGI, gas mass flow rate, mg given, specific heat of gas, Cp gas, inlet water temperature, water inlet, outlet water temperature, TWO, inlet water enthalpy, H water I, inlet water enthalpy, okay, this should be repeated, water mass flow rate, M water dot, outlet gas temperature I have to find. So, let us say I have one economizer, inlet temperature 255 and outlet gas temperature. So, T gas outlet is not given, inlet water temperature is given 40 degrees centigrade, outlet water temperature 170 degrees centigrade. Okay, water mass flow rate is given 5.75 and gas flow rate is given 49.86. Now, energy gained by the feed water, first energy gained by water, energy gain by water equals energy loss by gas. So, E gain equals m dot water equals H out minus H in. Okay, so it is becoming into 5.75 719.08. This will be outlet enthalpy. It is given as 719.08 kJ per kg. 719.08 minus 167.53. So, it is coming 3171.41 kilowatt. Therefore, the energy gained by water is this one. Now, energy loss by gas equals energy loss by gas. So, therefore, Q gain H2O equals Q loss gas equals 3171.41 equals MCP delta T. Therefore, 3171.41 equals 49.86. It is given the gas mass flow rate into 1.020505. It is given the specific heat of gas and temperature difference T in minus T out. So, therefore, T in minus T out gas equals 62.32 degrees centigrade. So therefore T out is coming 255 minus 62.32 equals 192.67 degree centigrade. So this is your answer. Another problem on economizer. An economizer has the following data: flue gas temperature entering 631, and it is actually counterflow heat exchanger. So first I have to draw a counterflow thing. There in flue gas temperature entering 631, because flue gas temperature will be higher than water temperature, so 631, and leaving 316, and enthalpy entering 149 BTU per LB H 1 T1 H2 equals enthalpy leaving 65 and T2 equals this. Flow rate also given, Q gas 245000, and T small t I am putting for water 284, and enthalpy H1 equals 255.3, and T2 equals 382. It is gaining heat, so temperature will be more than entering temperature. H2, maybe H water I can write, water, H gas, H2 gas. So H2 water is not given, okay, but flow rate is given. Q water is given 202390. Okay, these values are given. So economizer overall heat transfer coefficient also given, U also given 15, heated length 14 feet, and area of tube is given 1.75 feet square per feet. Number of tube rows, wide and high. Wide height means like this. Okay, I can assume this is wide and this is high. Okay, so how many rows are there? Wide means like 1, 2, 3, 4, 5. This is high wise, and wide wise like this. Okay, so I will have many tubes like this. So these are my tubes. The circle I am drawing, that's actually a tube. Okay. Number of tube high you have to calculate. So vertically how many tubes are there, you have to calculate. Assume inlet and outlet at the same end, heat exchanger type, counterflow. Same end means actually you have to use even number of tube. So how to solve it? To solve it, so flue gas entering temperature TF1 631, TF out 316 degree Fahrenheit. So you are taking degree Fahrenheit, so all must be degree Fahrenheit. So gas sensible heat entering, so H flue gas enthalpy 149 BTU per LB, and QG gas flow rate is given. QG is given 245,000 LB per hour, pound per hour. Feed water entering T water 1 284 degree Fahrenheit, T HW1 is given 255.3 BT British thermal unit per LB. So you should remember this units also, British thermal unit. Water flow rate Q water 202390 LB per hour. Feed pump discharge pressure, that is not required actually for calculation. Feed water temperature leaving, feed water temperature, so TW2 is given 382 degree Fahrenheit. Economizer heat transfer coefficient, overall heat transfer coefficient is given 15 BTU hour, feet, degree Fahrenheit. Heated length is given 15 and area per feet is given 1.75 per feet, and number of tube wide number of tube n wide is given 18, and n high we have to calculate, and they are saying this is counterflow heat exchanger. Okay, so counterflow means first you have to do this counterflow thing. Okay, going like this, and I already have written this 631 to 316 and entering 284 to 382. Okay, now del SG equals del QG equals QG1. I should not write Q, rather I will write H. Del HG equals HG1 minus HG2. So it will be giving 149 minus 65 equals 84 BTU per pound. Okay, feed water enthalpy rise del H. Del H water, how much water is taking energy from gas? It is del H water taking energy from gas. Now I can do the energy balance. Del H into W QW equals del Q gas into del HW del H gas. Okay, now this will be giving del H equals del HW will be del QS HG into HG into QG by QW. So this will be having 84 minus 245000 divided by 20390. So this is coming 101.7 BTU per pound. Now because this is counter flow heat exchanger, so the LMTD you have to calculate, logarithmic mean temperature difference. You can, to understand this one, you have to go to previous lecture, heat transfer. So T del T1 del T2. So del T1 minus del T2 divided by logarithm of del T1 by del T2. Okay, so what is my del T1? Del T1 is 631 minus 382 minus del T2 316 minus 284 divided by 284 divided by del T1 631 logarithm of minus 382 divided by 316 minus 284. So if I solve this one, if I calculate this one, then 105.6 degree Fahrenheit is coming. Now economizer surface area. Surface area given A. So therefore del QG WG equals UA LMTD. Okay. Now therefore A equals del Q not QG, I will write HG UA LMTD. So del HG into WG gas. Why WG? I am writing QG QG So yeah, I did not write W. Yeah, okay. So QG divided by LMTD. LMTD into U. So required number of tubes rows, number of tube rows high S LNWA equals, okay, so total heat transfer divided by LNWA. So this will be becoming 29.5. So number of tube rows, number of equals 30. Why 30? Because starting and ending at the same point, so it will be even number. So this problem is taken from your book Boiler Combustion, Marine Engineering book Marine Engineering by Harrington. Harrington, page number 125. Okay, so if there is any issue, just please try to go through the book. Thank you very much for today's lecture. Next day we will start new topic. Thank you.